for example, a cylinder, and then we wanted to decorate this in some way. First we triangulated it. We also heard that every triangulation is equivalent. After the triangulation, we take the Poincaré dual, and then the Poincaré dual can be evaluated by looking at it as a string diagram. So I think we had this today already. So we want to do the trivial defectivity of, do we have what is for example, of this. Alright, so who thinks they can read off the string diagram of this, like by a show of hands? Yes? Okay, so let's do it together. We want to go from bottom to top, so we start here. We have 3 starting points, which are all our Frobenius algebra A. And then we first have this loop. What's this loop? This is just the multiplication mu. So we have A times A. And then we have this again. Here we already see, okay, this is something we can associatively change if we want later. Then it continues on. What's this point? This 1a comes in and 2 come out. So this is the co-multiplication. And then here weird stuff happens, maybe. But we can just continue to look at what happens here. Let me do it like this. We have something over there, and now we have this going around the back side. This is just the braiding in the graphical calculus. So behind this, we're going to this, and this is a multiplication again. Going into the rest of this, and this is just the bottom part again, but with the co-multiplication. Okay. So we also called this P33 because we go from 3A's to 3A's. Now we can imagine, okay, maybe we have more A's here, and this is also plucked up. If we do this, we just get the general operators KL, and we write for the number of A's we have K and L. Alright. So maybe question, who knows how to read a string diagram? which directions. Okay, that's not enough hands. Let's try and read a string diagram together. We want to work with Frobenius algebras. So, for example, we want this identity to hold. Which is what?
No.
Ah, sorry. We want this identity to hold, of course. It was all a test. So the first step is to label the objects of our category. In this case, we only have one object, namely A. These are the inputs and outputs, if you want to say so. And now we want to read it from bottom to top. So what happens here is we have first nothing happens on both sides, so the identity morphism, and then here something happens. If we want to write it down algebraically, this thing is just bottom to top, right to left. So we go until we hit something. This is a morphism. What is this? This is the co-multiplication. Because we go from A to A tensor A. Right? But we don't write these because it would be very tedious. So first we have co-multiplication tensored with the identity on A, which is here, because we still have to remember something is here in the rest of the picture. And then the picture continues, so we have vertical composition. And now we have something from A tensor A to A, which is our multiplication, on the left side, and on the right side we have the identity on A. All right? Who knows how to read a string diagram now? Yes, okay, perfect. If you want, you can try to do the other one, but I believe you. All right. So, as a reminder, we had some exercises to do. The first one, I think, that makes sense to think about would be proving that these P operators can be chained together in a nice way. So a P from L to M after P of K to L is just P of K to M A's. Maybe you can try doing this yourself for maybe a few minutes. Try finding a starting ground. Remember, these are the operators we're talking about. And we only want to chain them together. So this composition just means we want, this is the first one and the other one is on top. Yes?
Is what you drew the simplest triangulation for 3 to 3, or could it be made simple?
No, I can, like the loop. You just take out the loop.
Okay. I'm not sure, to be honest. I think...
So it was stated in the lectures it's triangulation invariant, right?
Yes.
So basically my question is this like the nicest triangulation we could use or something?
I think so, yes. Because if you don't have 3 starting points here, it's not a simplicial complex.
Yeah, okay.
What if you take out that braiding thing in the middle? Is it like trivial then? What if it doesn't braid?
Then you would only have 1 2-stratum. That would be a triangulation of the cylinder.
All right, 3 minutes. All right, how's it going? Do you have an idea how to compose these and what happens? Any questions?
Would the general form basically be just? Oh yeah, no, yeah, you just explained that. I just.
Okay, perfect. Other questions? All right.
Sorry, can I just ask, like, what conditions do I need to like make a triangulation? I don't quite understand how I choose that.
To make any triangulation?
Yeah, sure.
Oh, well, you build it out of simplicial complexes, basically. I think the technical details are not necessary for this to compute anything here, but if you want to know more about it, maybe we can talk, or maybe Nils can talk about it.
So tomorrow I'll say a bit more about triangulations in general, but here in this two-dimensional case, we just glue triangles together along their edges. And if you do that, then you have a triangulation inside your manifold. But as Lorenz says, the main point is that when you choose a triangulation, because every triangle has precisely 3 edges, the dual to the triangulation will have vertices which are trivalent. And we decorate them either with the multiplication mu or the co-multiplication delta, and then something like this shows up.
So when you have to take like one triangle, and then because it's got 3 sides, you need a certain number to do a triangulation. Is that the idea? But if you do extra, you can reduce it down.
Right. So the question of how many triangles at least you need for a given manifold is complicated. I don't know the answer for a GSG surface, but behind that red picture that Lorenz drew is a triangulation that is not visible.
Yeah.
And the idea is that instead of focusing on the triangulations, is that we simply choose a network made up of A, mu, and delta, such that every two-dimensional component can be contracted. So it's just a disk.
Right.
Which is the case in this example, as you can check, and then we just work with this, and then the main point is that not so much what triangulations look like, but what the properties of mu and delta are. And they can be used to argue that this PP is equal to P is correct.
So, what should happen if you tried it yourself, or what can happen if you do it later, is that you see, first of all, I have an ending of one of the 2 P's that fits together with the other one, otherwise we wouldn't be able to compose them, which has L strands here, and we plop them on together, and then we end up with a middle of this whole thing that looks like this. So this is just this part glued together with this part of the other one. So we have L many strands here, and now you can imagine, okay, how do we proceed? We use the Frobenius algebra relations, and one of them is just that this is equal to this. So using this, we can just cross this out and have this instead. And now we can continue doing this until we only have one strand. which is then the middle of our picture. And then we're left with the ends, which almost looks like what we want. We would end up with something like this. So down here we would have K, and then we have this. And because we had to plop it on here, and all of these now vanished, but we still have this middle part of the other one. We have another one of these things here. So this is still here, and then the rest continues on like this. And on top here we have M strands. Alright, so this is nearly a p-type operator. The only thing that is left is to pick this middle part apart and show that this is the same as one of these. I will leave this to you because there's not much time. But you only need string diagram calculus and the Frobenius relations. Alright.
Sorry, can I ask a...
Yes.
I'm a bit confused about the difference between the actual cylinder and the string diagram, because there's no braiding on the Frobenius algebra, right? You haven't specified the braiding data. But in this picture, we are drawing like one over the other.
No, there's no braiding in the Frobenius algebra.
So what does it mean to untangle?
Well, it is symmetric braiding from vector spaces,
Yeah.
right? So it doesn't matter if you draw the line over or under. It's just to make it easier to read.
I see.
It's not structure of the algebra, it's structure of the ambient symmetric monoidal category, which is vector.
Thank you. Okay.
But in theory it could be non-symmetric, right?
In theory, it could be non-symmetric, but then the translation only makes sense if your cylinders are embedded too many folds. Otherwise, you can't decide if it was an over and under braiding.
Yes.
Maybe another comment. So you just suggested that it's a string diagram calculation that you show that this is indeed P and K. That's one way to do it. Or you don't do any calculation at all and just assume that it's true that what Lorenz says here is dual to a triangulation, and PMK is dual to a triangulation, and in the interior of that cylinder, at the boundary of the cylinder, they are the same. So there's only a change in the interior of the cylinder, but that's just a change of the underlying triangulation. And we chose the algebraic structure of this Frobenius algebra such that we have invariance. So if you believe the proof, then there's no computation that's necessary.
All right, any more questions for this? Yes?
Okay, I see that in order to get the relation, the thing that you need to do is rotate the top of the cylinder by 180. What exactly is the property of delta separable symmetric Frobenius algebra that I have to use?
Ah, okay. Well, a few of them. And you can't really think of this as a cylinder that you can rotate anymore because you're now in a string diagram. But all the properties of the Frobenius algebra, like this one, for example, which we had before, are helpful, but you can also just argue like Niels just did.
Sorry, so the question was it about this twisting on the cylinder. That is, what is it when you don't have the cylinder anymore? Okay, because it was the same question. To me, it makes no sense if there isn't a cylinder inside to draw like a thing like this.
Mm-hmm. Yes, that of course this is to draw it as a intuitive thing for us, but the braiding underlying doesn't need like an ambient cylinder for it to work. So
how do you interpret it then in more than 2D? Like if you don't have the cylinder, what does it mean that one line goes like in one direction and the other in the other direction if you don't have
you mean how you
something.
do higher string diagrams?
Yes.
Or, well, that's complicated. Of course. So the it gets less easy to use if you have higher dimensional string diagrams.
If I understand the question correctly, are you asking how to interpret this part of the string diagram?
Yes, if you don't have the cylinder inside.
Yeah, so there's no cylinder anymore, we just have this diagram, and this is a special, thank you. When we draw something like this, for any two vector spaces, V and W, for example, then this is a linear map from V tensor W to W tensor V. And what does it do? As we discussed yesterday, it sends a vector little v tensor little w simply to little w tensor little v, or direct sums thereof. So, and afterwards, if you were then to multiply them, then it just means that instead of multiplying v with w, you multiply w with v. That's what it means. And as Ingo said, it's symmetric, so whether we draw it like this or like this doesn't make a difference here. And to address your question, if you don't want to use the elegant proof, but want to compute it directly as an exercise, then you use the properties of the delta separable symmetric Frobenius algebra, but you also need to use at some point that the braiding isomorphisms, which I called beta VW here, so in particular beta AA is an example thereof, they are natural, meaning that we compose the braiding with the multiplication, and then here comes so any such thing, and then we can pull it through on the other side. That's what naturality means in particular. And then with a bit of playing around, you can prove it directly as well.
Other questions?
So to be clear, you need to turn that diagram, if we were doing the second way, into a single braid, right?
Yes. Right. Such that it has the form of the P operator.
Which is a nice exercise.
All right. So, since we know now that we can compose these P's and get a P out again, we also know that they are idempotents, like the PKK composed with itself is just PKK again. Right? This follows from this. And now we can deconstruct them by having projection and inclusion maps, which we draw like this, and if you want to draw them, which have these properties, of course. So I called this ZK here. This is just the image of PKK, rank K. What we now want to see is that the image of PKK is isomorphic to any other image of any other PLL. And we can show this by showing that the image of PKK is isomorphic to the image of P11. And this we can do by constructing an isomorphism directly. So this is a candidate, and maybe someone has an idea what the inverse could be.
Maybe it's helpful to write out what psi k1 is as a string diagram, then it's easier to visualize because it's visualized.
Let's draw a picture. So psi k1, written out like this, begins with iota k. So we start here. At the bottom we have zk. It's iota 1, sorry. So this is z1. And we go to we go further, and then we continue with pk1. So pk1. So this is iota k, and now we want to write out pk1. So it goes from 1a to via this grading thingy in the middle to K's, K strands. And so this is and now we want to continue with pi k, so the projection onto zk, so the image of pi kk. And this we write like this. This is okay. And now we can think about what might be an inverse of this. So I think you have the right idea. Do you want to try saying what it would be in terms of the algebraic?
I guess it would be pi k composed with p1k composed with I.
Yes. Oh, well, you have to switch the k's and the ones around. Then it works. So I'll try and fit it in here, maybe. So composing it, we would like to have something that has z1 here. And
if you write it right underneath, it will be easier to compute.
Yeah, I'm not sure if I have enough space for this, but yes. So this is all right. So this is also wrong. So we want here to have pi k. In the middle we still have z1. This works, so we can compose it. Pi 1, sorry again. Then we want the other p operator. So this works like this. And after the p operator, where we go from k to 1. We want the other inclusion to start all of this. And this is the k. All right. And now we can try to see why all of this produces the identity on zk. And if we can show that, then we have shown one way of the inverse of this formula. Yeah, and the other way works very similarly. Any ideas where to start? If not, that's fine, because this is just using our identities here now. So this, for example, is first pi1 and then iota 1. So this just gives us p11. If we think about this and think about what p11 looks like, what's left?
The braid.
Yes, only the middle part. So we can look at this thing here and say this is p11 and here too. But because these are idempotents, this is just p11. And then we have left zk at the bottom, one braid in the middle, and zk at the top with these parts still here. So what do we have left? Let's draw it. zk. All right. So, what does this look like? Well, we can see, okay, we have an inclusion at the bottom still and the projection at the top. And in the middle, we now have just pkk. Because the p11 is just the middle part of any pkk, and we have k strands up here and k strands down here. So all of this we can write out now. This is first iota k, then pkk, and then pi k. But since we know pkk is just equal to iota k after pi k, we can rewrite this like this. And this is just twice this. So if we just bracket, we get the identity on zk twice, which is just the identity. And now we're done. Does this make sense? Any questions?
ZK is a subset of A tensored K times.
Yes, ZK is the image of PKK.
So like that stuff at the bottom, it's not products and stuff. It's just a notation for the inclusion. Like those junctions on the vertical line.
It's a notation for the morphism iota K. So iota K is a linear map from ZK to A tensor A tensor A, and this is just a notation to write this in a. Yes.
The notation PLK, it doesn't really capture what the defects are doing in the bulk, right? It only cares about what is going in and what is going out. So it's not a single operator, it might be anything.
It's all the same operator, but there's lots of expressions for it.
But lots of...
It's a linear map.
Yeah.
PLK is a linear map, but it can either be represented in the way it is there, or you choose a much more complicated dual triangulation and you have a much more complicated string diagram. But because of delta separable symmetric Frobenius algebras, they're all the same linear map.
Other questions? Right, we don't really have much time. You want to add anything?
No, just ask whether there are any general questions.
What do these objects and projectors correspond to? If there is like a quantum field theory with an action, what will it be?
So we have this big vector space A to the tensor K, and then there's the idempotent or projector PKK, and you can think of it as a Hamiltonian which consists of commuting projectors. It's just one projector, so in dimension 1 plus 1 it's not very interesting. And then the ground states are precisely what it projects to. When we discuss in the Thursday lecture a three-dimensional version of this, then we rediscover Levin-Wen models or Carqueville models via a 3D version of this. Again, there will be projectors on state spaces for genus G surfaces, and they can be they come up in this general construction. But then one can explicitly check, as Ingo Vincentas Milevicius and Thomas Voss did a year or two ago, that these give Levin-Wen models and how to generalize them to other theories.
What would A be in a QFT? What would it correspond to?
Some auxiliary thing. It's not really a proper QFT. It's some input. So what we're doing with all these calculations is trying to get some experience in calculating with string diagrams, and with this choose a triangulation, go to the dual, evaluate, and so on. But what comes out, the last step that we did minus 30 seconds ago, is that the image of P11 is just the center of the algebra. So that's the commutative Frobenius algebra. You can either say start with the delta separable symmetric Frobenius algebra and wonder how you can gauge that symmetry in order to get a closed TQFT. You know, every closed TQFT is a commutative Frobenius algebra. So what's your guess how to get from a non-commutative delta separable symmetric Frobenius algebra to commutative Frobenius algebra? We just look at the abelian subalgebra, the center. And here we rediscover the center by going through this construction. But this construction does not only work in this particular instance, but much more widely. So we get some experience. And A, together with mu and delta, is the symmetry. So it's not, I take back what I said earlier. This delta separable symmetric Frobenius algebra is the not necessarily invertible symmetry of the trivial TQT.
So I just actually read to the exercises. What's what's a colimit? Because it's one of the exercises.
Yeah, limits and co-limits are universal constructions that you can consider in any category. An example of a co-limit is the image of an idempotent. That's the example that is relevant here. But also gluing Bordisms together is an example of a co-limit. And more generally, a co-limit is an object together with maps into the object, right? Into the object such that every other such, for a given kind of diagram in the category, such that every other such diagram factors through that thing. So it's a universal construction, like the tensor product of vector spaces can be described by a universal construction.
So it's the sport of the mathematician. You give me your favorite construction and I write it as a limit or a co-limit. Right? So that's like go ping pong.
Okay, thank you.
Eigenwert decomposition? Well, it's a kind of direct sum. That's a co-limit.
More questions or final words?
So if we were to write down a state sum model for a 2D DFT, then similar to what we saw in Lorenz lecture, where we would have this plucket operator. So are these idempotents thing that would sit in a Hamilton?
Yeah, that's exactly what I meant just now. So if we consider the 2 plus 1 dimensional version of this 1 plus 1 dimensional state sum construction, then we will also have some algebraic data that we put on the Poincaré dual of a 3-dimensional triangulation that I'll discuss on Thursday. And then there will appear some big vector spaces and some idempotents like this PKK and so on. And then computing the image of the idempotent means projecting to the ground states of the lattice model.
So on the continuum side of that conversation, I guess, I know if you have some 2D topological gauge theories, they fall into this framework, especially when you orbifold. But are there other kind of field theory descriptions for these theories? Not necessarily the trivial defect TKFT, they just mean 2D TKFT, as you've explained it. Are there other like field theory descriptions which aren't topological gauge theories? Like in the sense that it has a Lagrangian. So when you mentioned Landau-Ginzburg earlier or something, I don't know if that has a Lagrangian.
Yes, well, before twisting. So you're asking, are there 2D closed TQFTs which are not state sum models? Or are you asking which are not Dykov-Witten models?
I'm saying if they're state sums or not, are there 2D TFTs with interesting Lagrangians that aren't gauge theories?
Aha. Well, yes, there are.
Thank you.
But the Lagrangian is a bit different because it's just topological. So all the other examples of 2D DQFTs that I know are topological twists of n equals 2,2 supersymmetric quantum field theories. And then there's a BST operator, so a differential on the space of states. And then you can take cohomology, and it turns out that this cohomology is a commutative Frobenius algebra. And if you like, you can take such an ordinary supersymmetric sigma model or ordinary supersymmetric Landau-Ginzburg model, look at its action functional, and try and compute the path integral. Then there will a leap of faith will be necessary, but if you take that leap, then it will localize on the zero modes of the field, and the big path integral then literally reduces to a finite integral. So over a finite dimensional manifold. And this is how you can argue to consider the Dolbeault cohomology of a Calabi-Yau manifold to describe the commutative Frobenius algebra and supervector spaces that describes B-twisted sigma models, or the Jacobi algebra that describes Landau-Ginzburg models.
Thank you so much.
So maybe we have so further questions, please come to the front and discuss. So we have a little break now until 6, then we have our gong show, and after the gong show we will have pizza. So there's a lot of pizza, well I think it's a lot of pizza, I don't know. Then so don't run away, go to the gong show and then go to the pizza. And now thank you for the tutorial.